we're going to look at alternating series. Alternating series are where you have that kth term, and the terms are going to alternate in sign. So the a sub k term then is going to always include either a -1 to the kth power or a -1 to the k plus 1, or -1 to the k minus 1. There's various ways you can represent that. But what you're doing then is you're going to have every other term positive and every other term negative. So you're having that oscillation going on here between the terms. Now, if you look at the harmonic series, remember the harmonic series does not converge, so it diverges. And it's the sum of the 1 over k's, k starting with 1 to infinity. So that's 1 plus 1/2 plus 1/3 plus so on. If you put the -1 to the kth term, or k plus first term, and now if you use k plus 1 and the counter starts with k equal to 1, then the first term will be positive since it'll be -1 to the second power. So this particular series would be +1 minus 1/2 plus 1/3 minus 1/4 and so on. Just putting that -1 to the k plus 1 helps this series to converge. Okay? Now if you look at the graph here, we start with 1, so the very first term is up here at 1. Then we're going to subtract 1/2, so now we're going to be, the subtotal will be at 1/2. So we have 1, then we have 1 minus 1/2. These are the partial sums. S1, S2, the first two terms added together. S3 will be 1 minus 1/2 plus 1/3. And then S4 is going to be 1 minus 1/2 plus 1/3 minus 1/4. Okay, so as you add or subtract that next term, you're going to have these terms getting closer and closer together in the middle. Okay, now this is the sequence of partial sums in this graph for the alternating harmonic series. And you can see that as n gets larger and larger, as you go further and further, those terms are actually approaching some number there in the middle. Looks like approximately 0.7. Okay, so alternating signs can affect the convergence or divergence of a series. Okay, now the tests that we've run previously, if you go back and read the statement of them, they all said if the a sub k's were positive. The only test that we've used so far that we can actually use when the terms are not positive is the divergence test. So the divergence test is the only test that we've learned previously that will allow us, that can be used when we're using alternating series. So now there's one test other than the divergence test that we're going to use, and that's called the alternating series test. And it's very powerful so that you really don't need any of the other tests. So the alternating series test is what you're going to use anytime you get that alternating term, the -1 to a power, with the a sub k's. Now, you can still use the divergence test, though. So the divergence or alternating series test when they're alternating terms. Okay, so now this alternating series, -1 to the k plus 1 times a sub k. Notice here that the a sub k is separated from the -1 to the k plus 1. Okay? For this series to converge, the terms need to be non-increasing. So if the a sub k's are getting smaller each time, then we do have that the terms would be non-increasing. Okay, and it's just saying that a sub k is bigger than the a sub k plus 1. So the next term is always getting smaller or staying the same. Okay? At least once you've passed a certain point. If the first couple of the terms don't have that non-increasing feature, that's fine. But as you get further down the series, it has to be, the non-increasing. And if it's non-increasing and the limit of the kth term is 0. Now, if you remember when we did the divergence test said if the limit of the AKs is not 0, then we had that the series diverged. But we weren't able to use the divergence test to actually prove a series converges. But when you're talking about the alternating series, as long as the terms are non-increasing and the limit of the terms go to 0, then you do have convergence of an alternating series. Okay? So one thing to be careful of, don't get confused now, because on this one, alternating series, we can just check to see if the limit of each term is going to 0. This is the nth term. But that isn't true when it was just an all positive series. Okay? So for series with all positive terms, this limit going to 0 does not imply that it converges. But for an alternating series test that is non-increasing, it is enough to conclude that that series converges. Okay, now I want to look at these terms. If I look at every other term, my S sub 1 is up here. It's going to be, of course, the biggest term, because then we're going to be subtracting some things after that. And then now S sub 2, if this is a non-increasing series, that means that A sub 2 is going to be less than or equal to A sub 1. So if I'm going up to S sub 1 to start with, and then I'm going to subtract A sub 2, I'm not going to be all the way down to 0. I'll be subtracting less than what A sub 1 was. So I know that this partial sum has to still be something that's positive. I'm still going to be above the x-axis because I know A2 is less than or equal to A1. Well, likewise, when I go to add my A3 term to it, A3 is less than or equal to A2. It's smaller than A2. So if I came down from here to here, if this distance here was A2, and now I'm going to add back A3, which I know is smaller than A2, then I know I'm not going to get as high as I was up here. It's going to be a smaller number because I'm adding I'm adding less than what I came down previously. Each time, the amount that I'm going the other direction is smaller than what I went in the previous step. Okay? So that sum, whatever the sum is that these partial sums are converging to, must be in between this S1 and S2. Okay? In fact, it's always going to be between two consecutive terms. So as I go up and then come down, and now I'm going to go up a little less and then come down a little less, that sum, whatever that limit is for this series, whatever that infinite sum is, will be between two consecutive terms. Now, I want you to look at every other term now. Let's say I'm looking at S1, S3, S5, S7. Those, if I take just the odd terms, that's a non-increasing series. Notice they're going to be coming down each time. And it's bounded below. Okay, it's bounded below by whatever that infinite sum is going to be, or the previous term that we had in that partial sum. We know that if we have a monotonic series, so this one's non-increasing, that's bounded below, we know that it converges. Likewise, let's say we take the sequence that exists of the even numbers. So here's our S2, our S4, our S6, our S8. Those terms form a non-decreasing sequence, and we know that it's bounded above. It's bounded above by either the previous term or by whatever that infinite sum is going to be. So this also forms a sequence of terms that's non-decreasing and bounded above, and so we know it also has to converge. Okay? But what these two things converge to has to be the same, since those numbers are both a part of the same series, infinite series. So we know that that infinite sum is somewhere in between, in the middle here. And we know that those two, the odd ones and the even ones, both must converge. Okay, now we're going to look back at this alternating harmonic series again. The alternating harmonic series is just the harmonic series, but with this -1 term with it. Now let's see if it actually does converge. the two conditions we have to have met for an alternating series to converge is, one, it needs to be non-increasing. So I need to look at the a sub k's. Don't worry about the negative sign. The a sub k's is a sub k plus 1 less than or equal to a sub k. Okay? Now look at the a sub k. In this particular series, a sub k is 1 over k. Don't take the negative 1 part of it with the a sub k. The form of the series is minus 1 to a power, k or k plus 1, times a sub k. So a sub k is the part with that minus 1 term. Okay, so the a sub k here is 1 over k. Is it true that 1 over k plus 1 is going to be less than or equal to 1 over k? Now, if you want to actually give a formal proof, we know that k is less than or equal to k plus 1. And now taking the reciprocal of both sides inverts the inequality. So 1 over k then is greater than or equal to 1 over k plus 1. And this is a sub k, which is greater than or equal to a sub k plus 1. And so it is non-increasing. Okay, so we have condition 1's met. Condition 2, what about the limit of the a sub k's? Does it go to 0? Well, as k goes to infinity, we've got the limit of 1 over k, and clearly that does go to 0. So we would say by the alternating series test, sum of minus 1 to the k plus 1 over k does converge. Met the two conditions. Okay, so now let's see if we can apply the alternating series test on some other series. Notice here that the first term does have the alternating feature, that minus 1 to the k plus 1. So we know it's alternating, so that means you have two choices. You can either try the divergence test or the alternating series test. Now, the divergence test would only show us that something diverges. So let's go ahead and just use the alternating series test, because we're going to be checking the same thing, the limit of that kth term. So I see it's alternating. The next thing I want to check is it non-increasing? Trying to non-decreasing, non-increasing. Well, the term, the a sub k term, a sub k is 1 over k squared. A sub k plus 1 is 1 over k plus 1 squared. And obviously k squared, k is less than k plus 1, so k squared is less than or equal to k plus 1 squared. And that means if you invert them, 1 over k squared is greater than or equal to 1 over k plus 1 squared. So this one is the a sub k plus 1, and this one is the a sub k, so it is less than or equal. So it is non-increasing. And now the only other thing to check is the limit of the a sub k, don't worry about the negative sign, 1 over k squared, as k goes to infinity, is equal to 0. So all the conditions, it's alternating, non-increasing, and that limit of the nth term goes to 0. So by the alternating series test, sum of minus 1 to the k plus 1 over k squared converges. Okay, the next one. We aren't actually given what the kth term looks like here, but we can find the formula for it. If I look at this as my first term, k equal 1, now I'm going to think of that as 2 over 1. Here's k equal 2, k equal 3, k equal 4. I notice that the bottom number matches the k each time. The top number is always one bigger. So that means my a sub k is going to be k plus 1 over k. That's the general formula for a sub k. The series, because the alternating signs, it's negative 1. Now the first one needs to have an even exponent because it's positive. So I'm going to make it k plus 1 over times k plus 1 over k. Okay, and so this is going to start k equal 1 to infinity, and you can check to be sure that does give you that series there. Now, I'm going to rewrite that k plus 1 over k. It's hard to tell whether the a sub k's are getting smaller. I mean, you can see the top number is getting bigger here, but it's the whole term actually getting smaller than the previous one. So the easier way to actually check that is to rewrite that as 1 plus 1 over k by splitting it into two fractions. And now I can see that as k gets bigger, I know as k goes to infinity, k is smaller than k plus 1. And so 1 over k is bigger than 1 over k plus 1. So now add 1 to both sides. 1 plus 1 over k is bigger than 1 plus 1 over k plus 1. But this is just a sub k plus 1, and this one is just the a sub k. So I do have that a sub k plus 1 is smaller than or equal to a sub k. So it is non-increasing. It was alternating because of that negative sign. Now the only thing to check is the limit of the nth term. Let's see, my kth term, limit of my a sub k, will be the limit of the 1 plus 1 over k. Again, you don't have to worry about the negative sign. It's alternating. That's already taken into account. Now just look at the a sub k, the rest of it. And you can clearly see that this limit is not 0. That limit is 1. So the terms are not going to 0. So that would mean then that the alternating series test does not imply convergence here. Now, we can't use the alternating series test to say it diverges. We can say it doesn't look like it converges, but what we're really using here is the fact that the divergence test tells us that it diverges. So by the divergence test, since the limit of the a sub k's is not 0, then we know that this diverges. And we won't give it to in that form. Okay, so you use the alternating series test to tell if it converges or not, if it's alternating. But if that nth term is not going to 0, that's where the divergence test tells you that it diverges. Okay, now the last one. I have alternating, obviously alternating. I need to tell, is it non-increasing? That means that we want natural log of k over k to be getting smaller. Now that one's not easy to tell, and I can't split it up easily to be able to compare terms. So what I'm going to do is I'm going to take the derivative. If this is my function, then if I took the derivative of that, y prime, I'm going to have k squared k times the derivative of the top minus the top times the derivative of the bottom. So I've got that y prime is equal to 1 minus natural log of k over k squared. To be non-increasing, if it's non-increasing, that means that it's got to be getting smaller, which means it's got to be decreasing. This function, and notice if natural log of k is bigger than 1, will be negative. So y prime will be negative. If the derivative is negative, that means the function is decreasing. And if natural log of k is bigger than 1, then y prime will be negative. Well, natural log of k, I know natural log of e is 1, so as long as we pick a k bigger than e, so if k is bigger than e, then we'll have 1 minus natural log of k over k squared, which is the a sub k, is going to be negative. Well, we're not really talking about the a sub k's there. We're just talking about the derivative. Okay, so this will be negative, which means that the function is non-increasing or decreasing. Okay, so we checked the derivative there to make sure the derivative was negative. Okay, so now the only other thing to check, we know that this is non-increasing, alternating. Now just check the limit of the kth terms. So the limit of natural log of k over k. Now we've got a couple things we can do. If you try to evaluate, you'd get an infinity over infinity form, which then you could apply L'Hopital's rule, which would say that this is the same as the limit of 1 over k over 1 as k goes to infinity, which is 0. So the limit of the terms are going to 0. You also could have used the fact that in our growth table, natural log of k grows more slowly than k to a power, which we just have k to the first. So you have two options here, L'Hopital's rule or the growth table, to show that the limit of the kth term is 0. So that's true. So by the alternating series test, this series converges.